How the energy is stored in a capacitor. This is a capacitor, of the two plates, positive and negative, carrying charge plus Q and minus Q. To calculate the energy stored in this charge configuration, suppose initially this conductor is uncharged. Okay. Let some positive charge dq is transferred, charge be transferred from some external source to the first plate of the capacitor, and we go on transferring the charge, and at some instant, we go on transferring the charge dq, and at some instant, let on this plate the charge is plus q, and the induced charge is here. The induced charge here on this plate is minus q. And we go on transferring, it is continued, the process is continued. We are now again bringing dq over here. Now when plus, at any instant when the charge is plus q, so there will be a potential, this plate will be at the high potential because charge is plus q over this plate. So this plate will acquire a potential, we call it V. And what will be the value of V? Depend upon the capacitance of this capacitor, that is C. So Vc is equals to Q and V equals to Q by C. So this plate will acquire a potential V at any instant when the charge is plus Q. Now we are still bringing dq charge over here, because this is a positive charge, and we are also bringing positive charge. So there will be a repulsion between this and this. Against the repulsion, we have to do the work for bringing this charge over this plate. Now we are interested for finding that work done for bringing dq charge over here. And that work done will be small because we are bringing small charge. So small work dW, how much? Because you know what is the definition of potential? Potential is work upon charge. So dW upon dq. And work done will be, dW will be V into dq. V into dq. And substituting the value of V here, that becomes Q by C into dq. Now we are interested the total work done. This is small work done. Total work done when the capacitor is fully charged, mean when the charge is plus Q. So what is the total work done? Integrating. Remember, the work is done against the repulsion. So you have to do the work, and whatever the work done, it is stored in the capacitor, and that becomes the energy of the capacitor. That energy is called electrostatic energy. That energy is stored in the capacitor because work is done against these repulsive forces. Now we have to calculate total work done from 0 to capital Q. So 1 over C is outside, which is constant. Q dq integration is Q square by 2. And limits 0 to capital Q. Now substituting the limits, it becomes 1 over 2C into Q square. So this is the total work done. So total work done is Q square over 2C. This total work done becomes the energy stored in the capacitor. And the symbol of this energy is U. U is equals to Q square by 2C. Now there are another two expression for the energy stored in the capacitor, because if we are having the relation Vc equals to Q, So substituting this VC here, so V square C square upon 2C. So C and C cancels. So this is another relation, 1 by 2 V square C. Okay. Now then, this is the relation between Q and C. This is the relation between V and C. Now we are interested for relation V and Q. So eliminating C, C is equals to, you know what, Q by V. So substituting it here, so it becomes V square upon 2. C is Q by V. So V and V cancels. So it becomes the half Q into V. Half Q into V. So different relations are U is equals to Q square by 2C. And it is V square C by 2. And it is 1 by 2 V into Q. These relations, you remember all the three relations because you have to apply these different relations in the different numerical problems. Okay. Which relation, you will use, it depend upon the question. But you have to remember all the three.